So we're digging into module 3. And in module 3, we're really focusing on how can we use the derivative to gather information about what a function might look like. So we're going to focus over the next few assignments on getting information about the graph from the equation. So in the first part of this PowerPoint, we're actually going to do the opposite. We're going to get some information about the graph or about the equation from the graph. And then toward the end, you'll see kind of that switch from how can we analyze the equation to tell us what the graph might look like. Here's what I mean. We're really focusing on the extreme value theorem and the absolute extrema in this PowerPoint. So we're going to understand the extreme value theorem, locate local and absolute extrema from the graph. We're going to talk about critical points, and then we're going to talk about absolute extrema. So let's begin with this. This is one of those statements where mathematicians really try to make things more difficult than they should be. Excuse me, I had to sneeze. Hopefully it went away. We'll see. In math, we say, I was able to make my sneeze go away. Praise the Lord. In in the in math, we say that an absolute maximum on an interval at a c value, this c is going to be an x value. Okay, we have an absolute maximum if f of c is greater than or equal to f of x for all x. This is really, really intimidating if you read this. What we're saying is the absolute maximum has the biggest y value, of all other y values. Okay, so that, I mean, it really kind of makes sense, right, if we think about that. Okay, down here, the absolute minimum has the absolute smallest y value. If f has an absolute max or an absolute min, we say f has an absolute extremum at c. Now, again, there's a distinction we need to make, and it's this. These absolute max and mins occur, excuse me, there should be one R, occur at x values, okay? So if I say where is the absolute extreme, you tell me the x value. If I ask what that value is, then it's a y value. Let's take a look at a couple of graphs here. You'll notice that the y values keep going down and up in those two directions. And so there is no one y value that is bigger than all other y values, right? They keep going up and up and up and up and up. So notice we have no absolute max and no absolute min. In this case, we have a graph where the y values get bigger and then they start to get smaller again and approach zero. So this hump right here indicates an absolute extrema. It's an absolute maximum. The absolute maximum is 1 and it is at x equals 0. Notice that there is no absolute minimum because these y values are going to keep getting closer and closer to 0 but never touch it. Here's a case where I have an absolute maximum and two absolute minimums. Okay, so absolute maximum at 0, and then there would be another absolute maximum out here and another one out here, and that's what we mean by plus or minus 2 pi and plus or minus 4 pi. Here we have absolute minimums at negative pi and positive pi, and then negative 3 pi and positive 3 pi. So this is a periodic function, and that's why we have multiples of those. But you'll notice that the absolute minimum it says absolute minimum of negative 1. In other words, the absolute minimum is negative 1. The absolute maximum is 1, but it is at the x value. If f is continuous, remember continuity from that first module, right? If f is continuous over a closed interval. Now, a closed interval is one where we include the endpoints. That's what these brackets mean, include the endpoints. Then there is a point inside in between these x values where f has an absolute maximum over that interval. And there's a point where there's an absolute minimum. So basically, if you were to draw this, what it would mean is, well, that is not pretty at all. Let me redo that. If you were to try to draw what this looks like, this is better. Okay. A and B would be x values here. A and B would be x values. And I'm going to connect A and B randomly. Okay. I'm just going to go in and do like that. Okay. So this is supposed to have a little more curve to it. Okay. So this is continuous because I can draw it without picking my pencil up. This is f of A and this is f of B. And you'll notice that right here at f of b, there are no other y values in this region that are bigger than f of b. And down here, you'll see there is a y value right there that is smaller than the others, right? It's not sure what it is, but it is smaller than the others. It's really hard for me to draw with this pen, guys. I apologize. I'm doing my best. Let's see if I can undo those two. Okay. So this x value, right, where that minimum occurs, that absolute minimum, is in between A and B, okay? Now, the absolute maximum actually occurs at B. So again, our extreme value theorem says, this is one of the, this is the second one. We talked about the intermediate value theorem. This is the second important theorem here. The extreme value theorem says that there is a point inside this interval, including the endpoints, where the y value is bigger than all others and where it's smaller than all others. Now, here's a couple of exercises where we want to know, does the extreme value theorem guarantee the existence of an absolute maximum? And really the question is, which function is continuous on this interval, okay? So you would have to look and say, it says select all of the following functions for which the extreme value theorem guarantees the existence. This one right here is one where we might be concerned, right? We go from 1/2 to 3/2, okay? And if you imagine, are there any values in between that would make that 0, okay? So sine is continuous and cosine's continuous. So if you take a look right here, this thing is undefined when x is equal to 1, right? If we plug 1 in, we're going to have the cosine of pi over 2. And pi over 2, the cosine of pi over 2 is 0. So that's what leads us to a value where this is undefined. So 1 over cosine pi x over 2 is the one where the extreme value theorem would not apply. All the others would apply. Here's another one where we need to be aware, is this one going to be continuous at all places, right? Take a look at this square root. Can I take the square root of a negative number? Well, I can't, right? And if I plug 3 or 2 in for x, I've got 1 minus 2 or 1 minus 3. And those give me negative values. Down here, right, if I plug in 1, I get 1 minus 1, which is 0. 1 over 0 is undefined. So h and k are both functions that I'm concerned about. If you look, right, g and h are the ones that are continuous and the extreme value theorem applies. That means, what was it, f and k? Did I read that incorrectly? Let's see. Where did I miss? Let's see, 1 minus 4. Yeah, so I'm not sure why they included h in that. I'm fairly certain h is not. Let's talk about f though, because we need to identify what's going on here. If we have a value greater than 1 and we plug that into the natural log, right? So we'd have the natural log of 1 minus 2. Okay, so the natural log of -1. If you take the natural log of -1 on your calculator, you're gonna get an undefined value. So really, I believe function g is going to be the only one. So, those are some that you can take a look at in Newton. And if you have questions, please reach out. So there's another thing here that we want to be able to do, and that is look at a graph and tell kind of what's going on. Okay, so I'm not going to read that slide to you. I really just want to talk about these things here. Given the graph, what are the x coordinates of local extrema? Okay, and so from that previous one, a local extrema or a local max exists um, kind of on an interval, right? We're not looking at the very, we're not looking up here. Okay, so that wouldn't be a local max. That would be something outside of what we're talking about. A local max would be if I'm just looking right here, right? In other words, there's a hump. So we call that thing, it's not an absolute max. We would call that a local max. And there's another local max down here. There's a local max here. In other words, it's the top of a hump. And you can think about a roller coaster, right? If you're going down the hill and you go up. So there is a local min here and here. There are two local mins there at the bottom. Local min. And it says, what are the x coordinates of the local extrema? So to me, it looks like there's a maximum right here at 2, and then another one at -4. So I might say local max at x equal -4 and 2. And then those local mins occur right here at -6 and -2. So local min at x equal -6 and -2. You can follow along right here, and it kind of goes in, and they lump them all into one list, right? So it says the local extrema. The question didn't distinguish between local max and local min. It just said local extrema. So we want to list those max and mins together when you see that. Identify the x coordinate of the absolute minimum. Now we are distinguishing, okay? So the absolute minimum on the graph, the absolute, right? That's the one where we're not looking at the humps. We're looking at the very smallest y value. And that occurs right here where x equals -5. Okay, so the value is -7, but it occurs at -5. So here's where we start to shift the gears, going from looking at a graph to now looking at the equation, okay? Let C be an interior point in the domain of F. In other words, we have some value that is in the domain of whatever our function is. C is a critical point if F prime of C is 0 or if F prime of C is undefined. In other words, if I say find a critical point, we want to know when does f prime of x equals 0, or when is f prime of x undefined. Okay, so in either of those cases, we have critical points. Let's take a couple of examples here. So in this first example, I say, what are the critical points of this function? Well, I'm going to take the derivative, right? And the reason I'm taking the derivative is because I want to know when is f prime of x 0? When is it undefined? So 54 times 4 is 216, x to the third minus 8. I'm going to set that equal to 0 and try to find the values that make the derivative 0. 1/3 makes it 0. So we would say 1/3 is the critical point. It's really, really simple. First, find the derivative. Step 2, set the derivative equal to 0. Step 3, solve. Given this guy right here, find the critical points. So again, we find the derivative, we set it equal to 0, we solve, and that guy 5/4 is the critical point. Given the function x squared minus x minus 1, what is the absolute maximum over the interval -3 to 5? So we did this when we were looking at a graph, but we haven't done this where we're looking at an equation, okay? So what I'm going to do is I'm going to look for the biggest y value. Now, here's what I want you to focus on. I've got these points, -3 and 5. And I can connect those points, those y values, any way I want to. Okay. So I just randomly drew it like this. And what I want to know is what X value gives me the absolute biggest Y value? Well, in order to answer that, I need to know what the endpoints here are. What are those Y values? So if I plug in -3 to this, right? -3 squared is 9 plus 3 minus 1. Well, that's 11. And 5 squared is 25 minus 5 minus 1. 25 minus 5 is 20 minus 1 is 19. So my Y values of 11 and 19 are what I'm going to use to see, are there any bigger Y values or any smaller Y values? And here's what I want you to notice. These humps right here represent places where the Y values increase or decrease, okay? So the point is, I need to find out what is the Y value at this point and what is the Y value at this point. What we're doing is we're finding the critical points. We want to find the critical points and plug those in. We want to plug those into the original function. Okay, so because I want to know what is the Y value at those humps, all right? So I'm going to take the derivative, 2x minus 1. I'm going to set 2x minus 1 equal to 0, right? So 2x minus 1 equals 0. I'm going to move 1 to the other side and divide it by 2. So x equal 1/2 is a critical number. In other words, at 1/2, there is either a hump kind of like this, or there could be a hump kind of like that. Okay, so the critical number implies that there's some type of hump there that I need to be aware of. I'm going to plug 1/2 into the original function. 1/2 squared is 1/4 minus 1/2 minus 1. Or 1/4 minus 2/4 minus 4/4. And that's where we get -5/4. So here's what I know. Q of -3 is 11, Q of 5 is 19, and Q of 1/2 is -5/4. If we look at those, we can say that 19 is the maximum and it occurs at 5. We could also say that -5/4 is the minimum and it occurs at 1/2. But in this question, we were only focusing on the maximum. This one says find the absolute maximum for this function over the interval 0 to 3. And notice we're going to begin by plugging in the endpoints. So I plug 0 in for x, I plug 3 in for x, and I get 2 and 8. Take the derivative again. Now, the one thing I want to point out to you is that the derivative is not always 2x minus 1, okay? We just happened to do 2 problems where the derivative was 2x minus 1. So we're going to take 1/2 and plug it into the original function, like we did a few minutes ago, and we get 2, 8, and 7/4. The absolute biggest Y value is at 8. Okay, so remember, 1/2 is the critical point. 7/4 is the Y value of that. Okay. Now, if I said to you, what is f prime of 1/2, right? In other words, what do you get if you plug 1/2 into the derivative? You should tell me that you get 0. Because remember, we just set the derivative equal to 0 and we solved for 1/2. So we're plugging 1/2 into the original function to find out the Y value at that point. So we know that when x is 1/2, we have a Y value of 7/4, okay? And I have a graph that either does something like this, or it does something like this, okay? I don't know, all I know is that at that place right there, we have a derivative, we have a horizontal tangent line, okay? So I want you to go through these assignments. Let me know where you need some additional help. I feel like you're getting a good foundation here with the PowerPoints, but you know it's not going to answer all the questions. So please, please, please give me feedback on what additional resources you might need.